a quick summary. So what we've said so far is that whenever you hear the word derivative, you want to think of either the rate of change of something or the gradient of a curve, of a graph of a function, its steepness. Okay, and you need to be able to use these two definitions interchangeably, depending on the context, or actually, no matter the context, you should be able to interpret the derivative in both ways. Okay, so let's think about the rate of change for a second. The most common example is actually speed, because it's the easiest for us to think about rates of change in time. Yeah, when we use the word rate, we usually refer to time. So if something happens a certain number of times per second, it's usually what we refer to as rate. But think of velocity, for example. Think of speed. What do you mean if you say that you move with a speed of 20 kilometers per hour? Yeah, this line basically symbolizes the word per unit hour, right? What does this mean that you go 20 kilometers per hour? This basically means that at that given time, when you looked at your speedometer, it was showing 20. Yeah, but you might be accelerating, you might be decelerating, who knows? You might be trying to keep a constant speed, but it never is constant when you're driving a car or riding a bike, whatever, right? But at that given moment that you looked at your speedometer, it said 20 kilometers per hour. So this was the rate of change of the distance you traveled per unit time, right? So velocity in this case, or speed, we will be talking about the distinction in the future, but the speed in this case is nothing but rate of change of distance traveled. Yeah, where the word rate refers to per unit time. It doesn't always need to be per unit time. You might be working in, I don't know, marketing, and you might be thinking of how many customers you're going to get per each extra dollar spent on a certain marketing campaign. And then we will be talking about the derivative of number of customers with respect to the money spent on advertising. Okay, so this is the conceptual way of thinking. And now the second one, gradient, steepness, I think it's even more easy to think about because visualizing stuff is always easier, right? So if you have a graph of a function, right, this describes a behavior of something with respect to something. Yeah, we have an x-axis, we have a y-axis, whatever. But really, what we mean when we say steepness, we think about tangents. Think of tangents, where the tangents are basically lines that only touch the curve at one point. They do not intersect it. And we are very well familiar with lines. We know that lines have gradients. And when you draw a tangent, you draw a line, and the line has a gradient, which is equivalent, which corresponds to the gradient of the curve, in this case, the blue curve, at that given point where we drew the gradient. The tangent, sorry. So if I draw the tangent, for example, here, it's like a small bump, a maximum, you can see how the gradient would be 0. Yeah, if we now go back, yeah, this is a flat line. If we now go back to the definition, to the other definition of the derivative, rate of change, we can say that the rate of change of the function here is 0. It does not change because it flattens out, it levels out. For this very second here, where it approaches the maximum, same would be here. Right? So do look at functions now and try to draw a couple of tangents and comment on what the gradients of these tangents represent. Is the function increasing? Is the rate of change positive? So is the tangent, does the tangent have a positive gradient? Does it have a more positive gradient? Is it steeper? Or does it have a less positive gradient? Is it less steep? Okay. Is it decreasing? So now let me just erase these things. Is it decreasing maybe? Yeah, draw a tangent here. You can see it's decreasing. If it's decreasing, the rate of change is negative. Yeah, is it decreasing fast or is it decreasing slowly? And that is the geometrical approach. And one last thing to touch up on now is the notation. If the function here was to be called f of x, y equals f of x, then its derivative, so an expression or a graph formula that denotes its derivative, is going to be called either f prime of x, which basically symbolizes that we are talking about how the function f changes, what is its gradient, what is its rate of change, as we plug in different values of x's. So basically, what gradient does the function have at different values of x? An alternative notation, and it's equally valid. This is actually this is a convenient notation because it's very easy to just draw a simple little dash. However, this one is more explicit, where we say that derivative of some function, which we do as an operation, and we say that we differentiate. We say that we differentiate something with respect to x, and then we say what we're differentiating. We can put it in brackets, we don't have to. However, this is the important bit, another way of saying that we are representing a derivative. So you'll very often find notations where it, for example, says dy dx, and it also refers to the gradient of a function of a graph which is drawn in such a Cartesian plane, with y-axis being the usually the vertical one, x-axis being the horizontal one, and we're talking about what the gradient of this graph, of this curve is when we change x. So how does this function behave when we read it from left to right?